To the eye, the universe is a domain of stars and galaxies, a dazzling pageant of matter and light. But at a deeper level, the universe is governed by unseen forces that rule the fate of every star, planet, and particle of matter that space contains. Among these forces, the force of gravity plays a unique role. Only gravity operates on everything with mass, regardless of its distance, creating a mutual attraction between all the matter in the universe. From Newton to Einstein, the nature of gravity has preoccupied some of the greatest minds of all time. But beyond sheer fascination, there's another reason why scientists pay attention to gravity. These days, gravity isn't just a force, it's a tool that is allowing us to explore the universe and is showing us what telescopes cannot. Our gravitational exploration of the cosmos begins close to home. Made up of nearly 6 billion trillion tons of rock and metal, our own planet, Earth, has by far the largest mass and the strongest gravity that humans have ever experienced. In fact, Earth's gravity is strong enough to hold almost anything to its surface, including soil, water, and the very air we breathe. Even the moon, a sister world hundreds of thousands of kilometers away, is held in orbit by Earth's powerful gravitational pull. But Earth's gravity is not uniform. At different points and at different times, it can be slightly stronger or slightly weaker. For scientists, these tiny differences can reveal important information about the layers of rock that lie below Earth's surface, or about the movement of water and ice at the poles and around the globe, all of which have mass and contribute to Earth's overall gravitational pull. And the best way to measure these differences is not from Earth, but from space. This is the Gravity Recovery and Climate Experiment, or GRACE for short. Launched in March of 2002, it's a joint effort by NASA and the German Space Agency to map the subtle variations in Earth's gravitational field 1,000 times more accurately than ever before. GRACE is made up of 2 satellites, which orbit Earth in tandem and communicate with each other using a microwave ranging system. Flying about 220 kilometers apart, they make an exquisitely sensitive gravity meter. Whenever the leading spacecraft passes over a part of Earth where the gravity is a bit stronger, it feels a slight pull, causing it to accelerate and increasing the separation between the 2 spacecraft. Whenever the gravity is a bit weaker, the reverse happens, and the 2 orbiting spacecraft move slightly closer together. By repeatedly measuring these slight changes, GRACE has built up a detailed profile of Earth's gravity and revealed subtle variations across the planet's surface. Here, red represents areas where the gravity is slightly stronger. These correspond to mountain ranges and other large accumulations of mass. Blue shows where there is less mass, and the surface gravity is slightly weaker. Looking elsewhere, GRACE can also record changes that show more directly humanity's growing impact on the planet. In this view of India, red represents a decrease in gravity where groundwater has been drastically depleted by human consumption over the past decade. The quest to measure Earth's gravity with ever greater precision has become a key way to study our planet's hidden structure and monitor its ongoing transformation. But as fruitful as this technology has been, scientists have also come to realize that there are many more places besides Earth where gravity can be an aid to exploration. Now, similar missions are envisioned for other worlds, where we have far less information about what goes on below the surface. The first of these is already underway, and as expected, gravity is providing an exciting new way of seeing what was once hidden. For centuries, astronomers have wondered about the invisible mechanism that seems to keep the moon circling around us with clock-like regularity. It was Isaac Newton who solved the riddle. He was the first to recognize that the same force that causes an apple to fall from a tree is the one that keeps the moon in orbit around the Earth. He not only discovered the law of gravity, he understood it was universal.
5, 4, 3, 2, 1.
More than 300 years later, Newton's mathematical description of gravity is still used to calculate the flight paths of spacecraft that leave the Earth far behind, including those that set out for the moon. In September of 2011, NASA launched not one, but 2 identical spacecraft, both heading for a lunar rendezvous. This is the Grail mission. Its objective, to use gravity to unlock some of the moon's deepest secrets. Like the Grace mission around Earth, Grail is designed to monitor changes in the separation between 2 spacecraft as they are pulled in different ways by the gravity of the body they orbit. But compared to Earth, the moon is an even better subject for this double-barreled style of mission. The most important difference is that unlike Earth, the moon has no atmosphere. This means the 2 Grail satellites can orbit much closer to the moon's surface and, in doing so, make a much more accurate gravity map. At the beginning of 2012, when the 2 orbiters arrived, they were in highly elliptical orbits that took them more than 8,000 kilometers from the moon's surface, too far for useful measurements. But over the next 8 weeks, those orbits were carefully adjusted into tight circles with an average altitude of just 55 kilometers above the surface. At that height, the 2 spacecraft were tearing around the moon at 5,000 kilometers per hour, completing 1 orbit in just under 2 hours. And like a high-definition movie in Fast Forward, the stark lunar landscape rushed by beneath them. Scientists nicknamed the twin Grail satellites Ebb and Flow because of the shifting nature of the measurements they were designed to make. With Flow in the lead and Ebb about 100 kilometers behind, they circled the moon in formation so that if one felt a slightly stronger gravitational pull from one part of the moon, the distance between the 2 orbiters would change slightly. The probes kept track of their relative positions by sending pulses of microwave energy back and forth, while maintaining radio contact with Earth. Accurate clocks on board each spacecraft carefully tracked the timing of the microwave pulses, allowing the system to detect a change in the twin orbiter's separation as small as 1/10 of a micron, or roughly half the thickness of a human hair.
Experience the past like never before with History Hit's award-winning original documentaries and ad-free podcasts with our expert historians like Dan Snow, Susanna Lipscomb, Lucy Worsley, Mary Beard, Tristan Hughes, and myself, Matt Lewis. Sign up for an exclusive discount using the link in the description and embark on your historical journey from the wonders of ancient Egypt and the life of Anne Boleyn to the rise of Napoleon Bonaparte and the discovery of Shackleton's endurance. Get history wherever, whenever, exclusively on History Hit.
With this remarkable precision, Grail set out to explore the moon's gravity with 100 times the resolution of any previous mission. 1,000 times for the moon's less explored far side. In this view, the best ever of the far side, the side that always faces away from Earth, we see a rough and mountainous terrain packed with ancient craters. This is entirely different from the moon's near side, which includes large circular basins formed by asteroid impacts. Those basins are obvious on the near side because they are places where darker colored lava from the moon's interior broke through and flooded the surface. But the far side crust is much thicker, which apparently prevented lava from reaching the surface. With its careful measurements of the moon's gravity, Grail can see deeper into the lunar interior and help shed light on why the moon's crust is so lopsided. It may even shed light on a surprising theory based on computer simulations that suggests the moon's thicker far side crust was created in a collision with a second smaller moon. This epic crash would have splattered material all over the far side, like a giant bug hitting a windshield. But there are also deeper questions to answer, including whether the moon has now lost all of its internal heat, or whether deep down it still harbors a small molten core. To probe the moon to such depth requires data from all angles. It takes the moon 1 month to rotate slowly on its axis. So after 3 months of orbiting the moon from pole to pole, Grail gathered enough data to map the moon's entire gravitational field in exquisite detail 3 times over. Scientists are now continuing to analyze the treasure trove of data that Grail has provided, hoping for a definitive glimpse of the moon's mysterious heart. This is the promise of gravity as a tool for space exploration. It offers a way for us not just to see other worlds, but to feel what's happening inside them. Not even Isaac Newton could have dreamed of such power. A power that can also help us reach beyond the solar system and explore the cosmos in an entirely new way. For more than half a century, conquering space meant conquering gravity. Gravity was the obstacle that had to be overcome in order to leave our planet behind and travel to the moon and beyond. But even then, scientists knew there was another way to think about gravity, not as a barrier, but as a messenger that can carry information from the distant universe. This idea comes from Albert Einstein. Unlike Newton, who thought of gravity as a force between objects, like an invisible bond, Einstein reimagined gravity as a curve or warp in space. The warp is created by matter, and it also dictates how matter moves. Take Earth, for example. Because it contains a lot of matter, Earth stretches and bends the space around it, forming a kind of dimple in 3 dimensions. As the moon moves, it's guided by the way the space around Earth is curved. Instead of traveling in a straight line, the moon's path follows the curve and keeps circling around us. But this elegant way of thinking about gravity also has an interesting side effect. If space can stretch and bend, then space can also ripple, like a wave, a gravitational wave. According to Einstein, space is full of gravitational waves, like ripples on a pond, created whenever something with mass accelerates. But in practice, these waves are so slight that we don't notice them in everyday life, and we have no means of measuring them as they propagate through space. That is, unless the situation is extreme. And in our universe, there is no situation more extreme than that of a black hole. A black hole is an object with gravity so strong that not even light can escape. Yet even though black holes give off no light, their effect on the space around them can be strong enough to generate gravitational waves. The key is looking for places where black holes are accelerating through space and making big ripples as they go. One such place could be the center of a massive galaxy. It's now thought that most galaxies have giant black holes in their cores. Such a black hole may start small, but as it is fed by the galaxy that surrounds it, it can grow to the mass of 1 billion suns. Many of the largest and brightest galaxies in the universe are thought to have originally formed out of the collisions and mergers of smaller galaxies. If so, such galaxies could host not 1, but 2 giant black holes locked in tight orbits around each other. Because those orbits will eventually lose energy and decay, the black holes are locked in a death spiral, destined to collide. Drawn in by their mutual attraction, the 2 giants whip around each other at high speed. As they do, they generate massive ripples in space. Traveling outward, those waves will eventually sweep through our solar system, carrying information that could help scientists better understand the origin and development of giant black holes and their role in the history of the universe. But how to detect them? The answer is simply to measure space. Scientists have now begun to develop a measuring tool that will use lasers to detect minute changes in length across different distances in space. It's called LISA, the Laser Interferometer Space Antenna. LISA will consist of 3 spacecraft precisely spaced in a triangle that is 5 million kilometers to a side. Using laser beams to track their relative positions, they can detect a change in their separation down to 5 trillionths of a centimeter. Such extraordinary precision lies at the very limits of current technology. But it should be just enough to allow scientists to listen in on a universe that is filled with gravitational waves. What will it be like to perceive such a universe? Most of the time, scientists expect it will be like listening to a continuous buzz made up of waves from millions of black hole pairs located in galaxies scattered in every direction. But every now and then, there should be a much larger boom of gravitational waves created whenever 2 black holes finally collide and merge. It's beyond the ability of even the world's most powerful telescopes to witness such an extreme and violent event. But LISA could give us a front row seat.
Gravitational wave astronomy is so new that in a sense it hasn't even been born. That won't happen until a gravitational wave detector picks up its first real signal. But many researchers expect that moment is coming soon and that our generation will be the first to tune in to a whole new way of perceiving the universe.
As we do, we will again come face to face with a remarkable truth about our universe. Though it often appears vast and incomprehensible to the human mind, contained within its awesome beauty are the clues that will help us understand what makes the universe the way it is. A place where creatures like us can exist and explore. Traveling for hundreds of thousands of miles per day, yet always in sight of home. The product of a bold past, but also the bridge to an ambitious future. Designed to make spaceflight routine, it has taught us our most painful lessons about the danger that lurks whenever humans journey beyond our home planet. This is the legacy of the Space Shuttle, a vehicle that for over 3 decades came to define human spaceflight, while helping to create a permanent presence in orbit. But for scientists, the fleet of space shuttles also meant something more. They were traveling laboratories with access to the unique environment and perspective of low Earth orbit. Impossible to reproduce on the ground, this was to be the setting where astronaut researchers would test the limits of materials, the universe, and even their own bodies. all essential information that could one day help humans venture much farther into deep space. Of the 5 shuttles that blasted off from Cape Canaveral, only 3 remain. But despite the tragic loss of Challenger and Columbia, the program successfully completed 133 missions. And nearly 150 astronauts have flown in a shuttle, many of them making several trips.
The space shuttle may have completed its final journey, but over 30 years, it's managed to transform spaceflight by making it just a bit more routine, even as it's taught us that extreme exploration still comes with tremendous risks. The shuttle has also blazed a trail for science in space, a trail that continues aboard the International Space Station.
Today, the idea of a continuous presence in space in support of scientific research is no longer a dream. But it took the shuttle program to get there, and that took an act of true vision. In 1969, the same year that Neil Armstrong first walked on the moon, a small group of engineers in the California desert had a job to do. It was to build a vehicle to ferry people back and forth to low Earth orbit. Known as STS for Space Transportation System, this new kind of spaceship wasn't going nearly as far. And to be affordable, it would have to be reusable, a space plane that could survive both liftoff and re-entry. These early test models were dubbed flying bathtubs because of their clunky shapes. But what they lacked in grace, they made up for in stamina. Designed to deflect heat away from the crew cabin, the vehicle's wide underbelly was the key that would allow it to endure the searing, high-speed descent through the atmosphere over and over again. The final shuttle design included wings for stability, a feature that would allow the craft not just to descend, but to glide into a low-impact landing. The design was flight tested by releasing the shuttle from the back of a specially outfitted Boeing 747. But no flight test on Earth could reproduce the harsh environment of space. So, on April 12, 1981, the first of the shuttles to be readied for orbit sat poised on the launch pad.
6, 5, 4, we've gone for main engine start.
And as Columbia soared successfully into the sky, a 30-year journey for science on the shuttle was set to begin. With better access to space than ever before, researchers had a long list of topics they were eager to explore with NASA's new orbiter. And the first subject of serious study from the space shuttle was the one that was visible just outside the crew cabin windows: Earth. By now, views of our planet from a few hundred kilometers up were a familiar sight thanks to earlier chapters of the space program. But with bigger windows than the space capsules of the 60s and 70s, and with better technology to take advantage of that view, the shuttle raised Earth observation to a new level. This effort was already underway by the second space shuttle mission, which carried an imaging radar, a way of bouncing microwaves off of Earth's landforms to build up a detailed picture of our planet's diverse geography. The radar system proved to be a powerful tool for Earth scientists because, unlike photography from space, it worked regardless of whether it was imaging the day or the night side of the planet. It was also unaffected by cloud cover. Flying aboard the shuttle 3 times over the next 13 years, the radar system returned alluring and spectacularly colorful views of the surface. For scientists eager to study our world from above, there was no doubt the space shuttle had arrived, and it was showing them Earth like they'd never seen it before. It's said that beauty is only skin deep. But when it comes to imaging Earth from orbit, being able to see beneath the skin is a big advantage. That was the principle behind the space shuttle's imaging radar, which not only bounced microwaves off the planet's surface, but watched them penetrate a little way into the surface, allowing the system to see hidden information in the underlying rock and soil. Here, for example, a spectacular view of Mount Etna on the island of Sicily, one of the world's most active volcanoes. It reveals the complex succession of lava flows that have spilled down the mountain sides over many generations. Scientists compare images like these with what they observe on the ground and can use them to help explore more remote volcanoes from orbit. In another case, the dry, blowing sands of the Sahara Desert nearly conceal this curious geologic feature lying just below the surface. But because radar can penetrate the top layers of sand, this shuttle radar image of the Arunga crater in northern Chad shows what happened when a small asteroid collided with Earth hundreds of millions of years ago. The shuttle was used to study the possibility that the asteroid broke up into pieces before it struck, leaving not one crater, but a chain of at least 3 craters. Elsewhere, the same technology has also helped document more immediate changes. Here we see a shuttle radar view of Chile's vast and remote Patagonia ice fields, taken in October of 1994. In this view, red and purple indicate areas of high elevation. By comparing this image to one taken in the same shuttle mission, researchers were able to measure the speed at which different parts of the glacier are moving. Such measurements are crucial for understanding how Earth's icy regions are responding to global climate change.
We've gone for main engine start.
By the year 2000, the use of the space shuttle as a radar platform had evolved into the Shuttle Radar Topography Mission, which produced high-resolution elevation data for 80% of Earth's surface. The result was, at that time, the most detailed map of our world ever made. The space shuttle also explored our home planet in other ways. On 3 missions between 1992 and 1994, it carried the Atlas experiment, designed to measure the chemistry of Earth's atmosphere and its interactions with the sun. Among its many contributions were data that support the realization that chlorofluorocarbons, or CFCs, are damaging Earth's protective ozone layer, and that their production had to be curtailed. But this was just the beginning. Throughout the 1980s and 90s, the space shuttle offered a gateway for science and space of all kinds, especially science that could take advantage of the most obvious feature of space travel: the fact that in orbit, the concept of up and down seems to vanish.
The reason things behave so differently in low Earth orbit is also what makes it difficult for humans to work there: microgravity. As the shuttle orbits, it's actually falling around the Earth. Everything in it is falling too. Earth's gravity is still there, but its effects are no longer felt. This microgravity environment affects every aspect of spaceflight, from the design of the toilets to the way we might expect to grow plants for food in the future.
Without gravity as a guide, plants have no sense of down. Roots sometimes grow in the same direction as leaves. The effects of microgravity extend even to the smallest scales. In one startling shuttle experiment, salmonella bacteria were shown to become more active in space. Working with the space bacteria, scientists were able to identify the gene that switches on this behavior, a possible step toward developing a protective vaccine against salmonella, one of the most common causes of food poisoning. But humans are also not immune to the effects of spaceflight. In perpetual freefall, the gravitational cues that the body relies on for everything from muscle development to circulation to perception are gone. And while the sensation of flying in space can be liberating, at the physiological level, microgravity presents a severe challenge to the human body. One of many that must be surmounted before humans can live permanently in space. The space shuttle has been crucial to building up our understanding of what happens to the body when it's in space. But perhaps most important of all, starting in the late 1990s, the space shuttle became the essential tool for creating the International Space Station. A more ambitious and longer-lasting presence in space, and a stepping stone into the future. And with human spaceflight reaching for new heights, so too were the scientists eager to make use of the new facility to extend human knowledge into new frontiers. From the moment the first space shuttle took flight, humanity was on a new path. One that made low Earth orbit a familiar destination for an entire generation of astronauts. But the shuttle was, first and foremost, a vehicle, not a port. Even the longest shuttle missions were rarely over 2 weeks. To realize the full scientific potential of low Earth orbit for many types of experiments, researchers needed a permanent laboratory rather than an occasional visit. So, to establish a new outpost in space for a new century, NASA, the US Space Agency, teamed up with Russia, Europe, Japan, and Canada to create the International Space Station, one of the boldest construction projects in history. Of course, the shuttle would play a key role in building the station. Starting in 1998, it began ferrying up many of the modules and other elements needed for the giant habitat. In combination with the pieces lofted up by Russian Proton and Soyuz rockets, the massive station gradually began to take shape, reaching its completion only with the final few shuttle flights some 13 years later. During those years, the space shuttle became less available to scientists eager to pursue experiments in orbit. But the end result is something far grander and more versatile. By November of 2000, long before the station was completed, astronauts began arriving for the first long-duration missions to the station. The station has been occupied ever since, setting a new record for continuous human presence in space. In its current form, the space station accommodates 6 astronauts, giving researchers an unprecedented platform from which to conduct experiments in life sciences, materials science, earth science, and astronomy. And with a construction cost nearing $100 billion, NASA and the other partners behind the station are eager to get the most benefit possible out of the facility. In May of 2011, during what would be the second last space shuttle mission, astronauts delivered a final piece of scientific apparatus to the station. An unusual detector designed to probe some of the most powerful and mysterious energy sources in the universe. It's called the Alpha Magnetic Spectrometer 2, a device that counts and measures the high-speed particles coming from all directions in space, known as cosmic rays. It's thought the most powerful cosmic rays are generated by supernova explosions and giant black holes. But some may point to even more exotic processes at work in the cosmos. The trick is seeing enough of them to spot the types of cosmic rays that are truly rare. The vast majority of these particles are ordinary cosmic rays that are already well understood by scientists. But it's also possible that a very few of them will carry hints of an exciting discovery, possibly revealing whether other parts of the universe are made of antimatter, or else helping to identify the nature of the dark matter that astronomers suspect is everywhere around us, but completely invisible to ordinary telescopes. In more practical terms, the AMS-2 will give scientists their best information yet about the high-energy particle environment in our solar system. This knowledge is crucial for understanding how astronauts may one day avoid the hard radiation exposure that is one of the main hazards of a long interplanetary voyage.
Having fired the imagination of a generation, its place in history secured, the space shuttle pulls into port for the last time.
Following the final flight of the space shuttle in July of 2011, a new chapter was opened for the International Space Station. One in which private spacecraft, like the Dragon capsule built by SpaceX, take up some of the work of bringing supplies to the station.
With private companies servicing the space station, the hope is that NASA can move on to more challenging destinations, like taking humans back to the moon, or the asteroids, or Mars. Meanwhile, the International Space Station will continue to provide a platform for science in space. Some wonder if the station has been worth all of the trouble and expense to build, but its true legacy may be in setting the stage for a longer-term human presence in the solar system.
Oh, this is fantastic. Looks nice. Nice.
Stark desolation or breathtaking beauty. The planet Mars offers both at once, and much more. No other world has so captivated human imagination, and apart from Earth, no other planet has been more closely examined or studied. Yet Mars continues to defy our expectations. And the closer we look, the more we realize we barely know Mars at all.
The act of exploring another world is a plunge into the unknown, but Mars is different. So many spacecraft have been sent there that by now its major features are as familiar to scientists as the continents of the Earth. Today, the real unknowns on Mars are found at a smaller scale, a human scale, and exploring them takes a keen eye for detail.
Today, there's no keener eye on Mars than the one that belongs to MRO, the Mars Reconnaissance Orbiter. Like a great bird scanning for prey, MRO soars over Mars with its solar panels outstretched, using the most powerful camera ever sent to another world to peer down at the alien terrain passing below. As it orbits from pole to pole, MRO scans the surface, creating images in long strips that are only a few kilometers wide, but could stretch to well over 100 kilometers long. Within these narrow strips, MRO's sensitive camera can perceive features as small as a dinner plate. That's many times sharper than any previous spacecraft has ever seen Mars from orbit. And it means that MRO is the first orbiter with the power to connect the Mars we see from space with the Mars we wish to explore on the surface. Painted in false color images that are chosen to bring out interesting features, MRO's views of Mars are views at the level of local geography. But taken together, the small-scale details they reveal help to tell a very big story, both about the planet's current conditions and the ancient processes that produced this astonishing landscape. And because those processes involved heat and water, it is also possible that billions of years ago, they enabled the emergence of life on Mars. If life once did gain a foothold here, the evidence is buried under layers of Martian rock, layers that MRO can discern better than any other orbiting spacecraft. In fact, MRO has turned Mars into a planet of layers, allowing scientists to explore Martian history as though it were the skin of a giant onion. MRO has also shown Mars to be a planet sculpted by wind, where fine-grained dust can form vast fields of dunes that gradually migrate across the planet. The dunes of Mars are spectacular, rippled masterpieces that remind us of nature's power to create and destroy entire landscapes one sand grain at a time. With their shifting, sinuous features, the dunes bring Mars to life, revealing the dynamic nature of its surface. But the wind can also create phenomena that are much more fleeting. In many regions of Mars, MRO has found dark streaks crossing the plains, like scribble marks from a giant pen. These are the tracks left by dust devils, wispy whirlwinds that traipse across the surface like miniature tornadoes, scouring the rock clean of dust as they go. Dust devils are so common on Mars that MRO has captured several of them. Here, one twists serpent-like above the plain, casting a long shadow that reveals the dust devil is nearly a kilometer high. Elsewhere, there is a different kind of evidence that Mars can be the scene of dramatic action. Here, the spacecraft examines a crater that was not present in a 2009 photo, but appeared in 2011. In false color, the freshly excavated debris of the blast looks bright blue against the dusky surface. These fresh impacts are not just curiosities. The material they expose provides clues to what lies just below the Martian surface. And sometimes they can even expose a hidden layer of ice, the frozen remains of Mars's warmer, watery past. MRO has also seen plenty of ice sitting on the surface of Mars, but this is dry ice, made up of frozen carbon dioxide rather than frozen water. As it comes and goes with the seasons, the dry ice can take on a fascinating diversity of forms, sometimes appearing as though painted on the Martian surface by an artist with a flair for the improbable. And sometimes the view of a Martian polar terrain covered with dry ice can even seem to resemble bacteria under a powerful microscope. So powerful is the eagle eye of MRO that it has even been used as a telescope to look up at the two moons of Mars, Phobos and Deimos, as they orbit high overhead. These moons may someday serve as outposts, where human astronauts arrive before descending to explore interesting sights on the planet below. By then, the surface of Mars will have been scouted and sampled by a new generation of robot explorers. And those robots will be looking to MRO to tell them where to land. On the smooth slopes of Pavonis Mons, a giant Martian volcano, the Mars Reconnaissance Orbiter makes a startling discovery. A small crater, alone on the featureless landscape, appears to have a strangely dark center. Looking more closely, MRO finds that what seems like a crater is really a natural skylight, where part of a volcanic formation has collapsed, exposing a hidden cave below. This remarkable picture invites the tantalizing prospect of someday entering the cave and exploring Mars beneath the surface. But falling into such a hole unexpectedly would spell disaster for a rover on Mars. And that's why orbiting missions are used to spot both the hazards and the opportunities on the Red Planet.
When it comes to Mars, every orbiting spacecraft has two jobs. The first is to explore the entire planet from above, gathering the clues that researchers need to put together the story of the Red Planet on a global scale. The second job is to pave the way for exploration on the surface of Mars by finding the perfect place to land.
With its high-powered view of the surface, MRO has played a key role in the planning of missions to land on Mars, offering more information about potential landing sites than once was ever thought possible. In the history of Mars exploration, this is still a recent development. In fact, two of the best-known Mars explorers, NASA's Spirit and Opportunity rovers, had already been working on the surface for years before MRO arrived. Amazingly, MRO's vision is sharp enough to spot the rovers on the surface, although each is not much larger than a wheelbarrow. Here, the orbiter zooms in on the rover Spirit, which gleams brightly as sunlight reflects off its solar panels. Meanwhile, over on the other side of Mars, MRO finds Opportunity perched on the rim of Endeavour crater. With a diameter of 22 kilometers, this is the largest feature Opportunity has explored to date. It headed this way after MRO saw evidence for minerals related to water in its orbital view of the crater. Soon after MRO reached Mars in 2006, it had its first assignment helping a surface mission find the best landing site. The mission was Phoenix, a lander designed to touch down in the north polar regions of Mars and probe for the permafrost believed to lie just below the surface. Prior to MRO's arrival, mission planners favored an area known as Region B for Phoenix's landing site. But with their improved view from MRO, they found that Region B was full of boulders that would have spelled disaster had the lander set down on one. Instead, a backup landing site was chosen, and Phoenix landed safely in May of 2008. Soon after, MRO was able to confirm the lander's position by imaging it from space. For the first time in history, a landing on Mars had come with its own eyewitness. The next mission to Mars was to be much more complicated. Instead of a lander, NASA had decided to send another rover to follow up on Spirit and Opportunity's impressive finds. This newer and much larger rover was to be the most sophisticated probe ever to set down on Mars, an entire mobile laboratory. And it might be the first to determine if Mars once had conditions suitable for life. And with only one rover to land, there would be no second chances. MRO set about scouring the planet, helping pinpoint geologically interesting locations. As with earlier missions, high priority was given to places where there is evidence for past water flowing on the surface of Mars. Starting with a list of more than 60 candidate landing sites, scientists began a detailed 5-year investigation to find the best possible location for the next rover on Mars. Using data from all available orbiter missions, but relying especially on detailed views from MRO, scientists managed to narrow the list to 4 finalist sites by the spring of 2011. Among them were some of the most intriguing and geologically complex places on Mars. Places such as Holden Crater, an ancient formation that was turned into a vast lake when a channel carrying floodwaters breached the crater rim. Just north of Holden is another candidate site, Eberswald Crater. It also shows signs of past flooding, but here the key feature is an ancient river delta at one end of the crater. A very different kind of landing site presents itself at Marth Vallis. Billions of years ago, this channel drained a torrent of water from the Martian highlands in the south to the low-lying northern plains. All 3 of these sites show terrific potential for uncovering the history of water on Mars. But in the end, scientists chose a 4th site, a site that combines some of the most attractive features of all the others in one location, and adds a mysterious mountain that could unlock the secrets of ancient Mars. After more than 40 years of interplanetary exploration, Mars has offered some of the most spectacular sights in the solar system, from huge volcanoes to deep chasms to the beautifully sculpted layers of ice and dust that cover the Martian poles. But among its many diverse and intriguing features, there is nothing on Mars that looks quite like this: a giant mound more than half the height of Mount Everest, sitting squarely in the middle of an ancient impact crater. This is Gale Crater, a formation that has long attracted interest and speculation from Mars scientists. It's also the landing site of the most ambitious mission ever to touch down on the Red Planet, NASA's Mars Science Laboratory, better known as the Curiosity rover. Compared to previous rovers, Curiosity is built like a tank. The size of a small car, it weighs 900 kilos and carries 10 separate scientific instruments for the detailed testing of the rocks, soil, and atmosphere of Mars. But most importantly, Curiosity is powered by a device that generates electricity from the radioactive decay of plutonium. Curiosity's nuclear power supply would give it the potential to explore Mars for years, allowing scientists to select a more ambitious target. And few features on Mars are as scientifically interesting as the mountain in Gale Crater. Nicknamed Mount Sharp after a pioneering planetary scientist, this strange formation rises above everything else around it, including the rim of Gale Crater. Closer inspection by the Mars Reconnaissance Orbiter has revealed that the mountain is really a pancake stack of sediment, whose lowest sections are made of clay layers that formed in the presence of water. Those layers could well be a gold mine for scientists because they represent a slice of geologic time that spans over 100 million years of the most crucial period in Martian history. A time when Mars may have shifted from a habitable planet to a frozen desert. By July of 2011, Curiosity's fate was sealed. NASA announced that their new rover was destined to become a mountain climber.
3, 2,
The rover would be sent to Gale Crater.
and liftoff.
Now, it just had to get there in one piece. After years of planning and an 8-month journey from Earth, the moment of truth arrived on the night of August 5th, 2012. Nested safely in its protective capsule, Curiosity jettisoned its cruise stage and, drawn by the planet's gravity, began its terrifying plunge. Soon, friction with the thin Martian atmosphere began heating up the front of the capsule to a peak temperature of over 2,000 degrees Celsius. Now, still traveling at over 1,400 kilometers per hour and just 11 kilometers from the surface, Curiosity deployed its parachute. 15 seconds later, the heat shield fell away, revealing the rover tucked inside. But now, the rover was still falling fast when it separated from its parachute and back shell and ignited 4 powerful descent rockets. But how exactly to land? Separating from its descent stage, the rover was lowered to the surface on 3 nylon cables. As it touched down, the cables were cut and the descent stage veered off, crashing to the surface a safe distance away. And then came the signal.
Curiosity is the 7th mission to land successfully on Mars, but it's different from all its predecessors in a crucial way. It is the first Mars mission to combine the mobility of a rover and the scale and complexity of a field laboratory with the potential for operating for years on the planet's surface. That combination will change our understanding of Mars forever.
This will be the longest journey ever attempted on another world, but it will not be as lonely. As Curiosity begins its epic trek across the surface, it will be watched from above by MRO, the eagle eye that has become part of day-to-day life on Mars, even as we look for signs of life in the past. On a dark, moonless night, a misty light reaches up across the sparkling vault of the heavens. At first, it looks like a cloud or a puff of smoke that could blow away on a stiff breeze, but it holds to its place among the stars. Because this is something more permanent and more intriguing than a passing cloud. This is what the Romans once called the Via Lactea, the Milky Way. And for astronomers through the ages, it has proved to be a pathway to discovery.
To ancient skywatchers, the Milky Way was a mystery that became a myth. Some saw it as the wake of a celestial ship, others as the seam where the two halves of the sky were stitched together. But these stories and legends say more about the people who told them than they do about the true nature of the Milky Way.
To the ancient Greeks, the Milky Way was formed when the goddess Hera awoke to find a strange infant, the baby Hercules, suckling at her breast. The divine milk bestowed immortality, but when Hera realized she'd been tricked, she pushed the babe away, and the spurting milk sprayed across the sky. Today, our word galaxy comes from the Greek word for milk. But stories aside, the Milky Way's true nature was hidden until people could see it through a telescope. It was 1609 when Galileo first turned the new invention toward the Milky Way's misty light and recorded what he saw. Galileo had discovered that the Milky Way is made up of countless stars, stars that are too far and too faint to see individually. Yet together, they paint the sky with a luminous glow. It was a realization that changed everything because it gave depth to the night sky. And it meant astronomers were free to explore a heavenly realm that the ancients had never dreamed of. Galileo noticed that the stars in the Milky Way are sometimes grouped in clusters. And as telescopes improved, astronomers discovered something else. Clouds of glowing gases called nebulae that would later prove to be the birthplaces of stars. Many of them located along the Milky Way, like gems on a cosmic necklace. But even as the telescope uncovered the hidden treasures nestled within the Milky Way, it left a big question unanswered. Why is the Milky Way confined to a narrow band that wraps around the sky? It would take another century and a half after Galileo before someone had the beginnings of an answer. In 1785, William Herschel, a German-born musician and astronomer working in England, was already famous for his discovery of Uranus. It was the first planet in the solar system to be spotted with a telescope. Now Herschel was ready to turn his attention to the placement of the stars around the sky, including the Milky Way. His strategy was straightforward but painstaking. Pointing his telescope at over 600 different locations, Herschel proceeded to count all the stars he saw in each region, and he estimated the relative brightness of each star. Herschel guessed that fainter stars were further away than brighter stars. So when he put it all together, he came up with a picture of the universe that looked like this. It shows that we are embedded in a vast system of stars that has a flattened shape, like a giant millstone or a disk. In some directions, the stars are relatively few in number, but along the midplane of the disk, the stars become more numerous, their light adding up to form the glowing band of the Milky Way. Herschel's map was a huge step forward, but it was also just the tip of the cosmic iceberg. For beyond the limits of Herschel's telescope, a far grander Milky Way was still waiting to be discovered. By building on the work of William Herschel, astronomers in the 19th century had verified that our solar system is located within a galaxy of stars, shaped like a giant disk. This explains why the Milky Way appears to us as a glowing band of light stretching across the sky. When we look along the band, we're looking into the disk. But astronomers were not entirely satisfied with this early picture of our galaxy. For one thing, it meant the solar system had to be located near the center of the Milky Way, an unlikely coincidence. And without a way to measure the true distances to the stars, there was no way of knowing how accurate this picture of the galaxy might be. To get a deeper understanding of the Milky Way, astronomers needed new tools and new ideas. By 1912, they had both. The new idea was a way to directly measure distance in deep space, and its discovery was entirely unexpected. In the era before electronics, Henrietta Leavitt was one of several women employed by the Harvard College Observatory to do mathematical calculations. At that time, large amounts of data were flooding into the observatory, thanks to the development of astronomical photography. The female computers who worked at Harvard were not expected to make scientific discoveries of their own. But that is precisely what happened when Leavitt noticed a pattern in a certain type of variable star called a Cepheid variable. Leavitt saw that each Cepheid pulsed with a regular cycle, and that the length of the cycle was related to the total amount of light coming from the star. Simply by timing the pulsations of a Cepheid variable, astronomers could now calculate the star's true brightness, and then work out its distance by comparing that to how bright it appeared in the sky. The method was quickly put to use with the help of astronomy's most powerful telescope of the time, the 60-inch reflector high atop Mount Wilson near Los Angeles. Backed by the telescope's unprecedented power, Harlow Shapley, a crime reporter turned professional astronomer, would make galactic history. Shapley used the giant scope to examine globular clusters, distant concentrations of stars with a distinctly spherical shape. Each globular cluster contains hundreds of thousands or even millions of stars, circling around one another like bees in a swarm. Shapley believed that these clusters, in turn, must circle around the gravitational center of the Milky Way. By using Cepheid variables to measure the distances to the clusters, Shapley was able to work out the location of a point in space around which all the clusters appeared to be concentrated. The result changed everything. It showed that the real center of the Milky Way is located tens of thousands of light years away from us, in the direction of the constellation Sagittarius. For astronomers, the revelation was a cosmic wake-up call. Centuries earlier, it was Nicholas Copernicus who had nudged Earth out of the center of the solar system and put the sun there instead. Now it was Shapley's turn to push the solar system away from the center of the Milky Way.
Shapley's discovery relegated us to the suburbs of a galaxy that is much larger than anyone had previously imagined. Today, astronomers estimate the Milky Way is more than 100,000 light years across. Yet even in Shapley's time, there was growing evidence that this vastly expanded Milky Way was only a small piece of a far grander cosmic reality.
That evidence came in the form of a class of faint, fuzzy objects scattered around the sky that were coming into focus as telescopes improved. Many looked like little spindles. Others had a distinctly spiral shape. To some, it seemed that these faint swirls must be newborn solar systems forming within the Milky Way. But there was also a more radical possibility. Could they instead be other galaxies, like the Milky Way, but located far off in the cosmic distance? In the early 1920s, astronomer Edwin Hubble was able to prove that the answer was yes. Using the newly built 100-inch telescope at Mount Wilson, Hubble zoomed in on the largest of the mysterious spirals, the Great Nebula in Andromeda. There, he spotted Cepheid variables, the pulsating stars that would again prove crucial. This time, they allowed Hubble to calculate the true distance to Andromeda. The results would become a turning point in our understanding of the cosmos. Hubble's measurement showed that Andromeda must be a separate galaxy, far beyond the borders of the Milky Way. Today, astronomers have pegged its distance at more than 2 million light-years away. Other galaxies are millions, even billions of light-years farther. Hubble had discovered the rest of the universe. But he had also given astronomers a new way to think about the Milky Way by comparing it to other galaxies. The era of galactic exploration was about to begin. By the mid-1920s, astronomers had realized that the universe is full of galaxies. Like islands in a cosmic sea, the galaxies are separate systems, each containing hundreds of billions of stars. But this revelation raised many new questions about our own galaxy, the Milky Way. Was it a spiral system, like some of the others, that could be seen from afar? And if so, how would we know? It had taken centuries for astronomers to figure out that the Milky Way is shaped like a large disk, with the solar system located about 2/3 of the way from the center. Now the challenge was to map the Milky Way from the inside. This was no easy feat, and a big part of the problem is dust. Even ancient astronomers could see the Milky Way does not have a uniform appearance across the sky. Instead, it looks patchy and uneven. In some places, it seems split by dark rifts. This is because the Milky Way is interwoven with vast clouds of interstellar dust that block much of the galaxy from our view. Yet despite this visual barrier, there are clues that helped astronomers discern our galaxy's true shape. Among the first to follow those clues was American astronomer William Morgan. In 1951, Morgan was working at the Yerkes Observatory northwest of Chicago, where he was studying blue supergiant stars, the hottest, brightest stars in the galaxy. One night, while looking in the direction of the constellation Perseus, Morgan realized that a number of the giant stars he had been studying in that part of the sky were all located at about the same distance, between 5,000 and 8,000 light-years away. And so too is the Perseus double star cluster, a well-known feature in the same part of the sky. Morgan realized that the double cluster and the giant stars together traced a line through space, as though marking a structure embedded within the Milky Way. He had discovered the Perseus Arm, one of the great spiral arms of our galaxy. Before long, other familiar sites scattered along the Milky Way were also shown to be part of the Perseus Arm. Among them is the spectacular Crab Nebula, the remnant of a supernova explosion that was recorded in 1054. But if there was one spiral arm, there should also be others. By looking in the opposite direction from Perseus, astronomers found they could see traces of another arm that is located closer to the center of the galaxy. This is the Sagittarius Arm, home to a dazzling array of star clusters and nebulae that adorn the southern Milky Way. Spectacular sights, like the Trifid Nebula, make this part of the sky a visual paradise. Closer to home, astronomers have determined that our own solar system is part of the Orion Arm, a smaller structure that may be no more than a spur branching off of Sagittarius. Yet the Orion Arm, too, is loaded with amazing sights, which loom large in our view because they are relatively close by. It is when we look down the length of the Orion Arm that we see the nearest, and to us, the most spectacular star-forming region in the sky. The Great Nebula in Orion, where thousands of new stars are being born before our eyes. Aided by radio telescopes and infrared satellites that can see through the galaxy's obscuring dust, astronomers have now peered deeply into the Milky Way to map its structure in detail. They have detected more arms and also confirmed that the Milky Way is not just a spiral galaxy, but a barred spiral. Barred spiral galaxies are common in the universe. Their elegant appearance is the product of an evolutionary process that causes material within the galaxy to form a horizontal bar running across the center. Now, more than 60 years after Morgan's initial discovery of the Perseus Arm, astronomers can show us what the Milky Way might look like if we could view it from the outside. This is the result. An artist's view that shows our galaxy as a barred spiral with two prominent arms. One of them is the Perseus Arm, the first to be mapped. On the opposite side is the Scutum Centaurus Arm. It's much harder to make out from Earth, but astronomers have found that it hosts massive clusters of hot young stars, like this one, imaged in infrared light by the Spitzer Space Telescope. Completing the view are the lesser spiral arms that wind their way between the two larger ones, including the arm where our own solar system is located, right here. This is a view that no telescope can show us, but one that is supported by years of observation across the entire Milky Way. The mapping of our galaxy is one of astronomy's great achievements, but it's more than just a map, it's a snapshot of a dynamic star system with a history that has unfolded over billions of years, a history that relates directly to our own existence. In that sense, the spiral may be the ultimate cosmic symbol of life, for it's in spiral galaxies that new stars and new planets are born. It's the same process that led to our own solar system's creation in the Milky Way. In that sense, the spiral may be the ultimate cosmic symbol of life. For it's in spiral galaxies that new stars and new planets are born. And sometimes civilizations like ours, with a desire to map and to explore the universe around them. In all of human experience, there are few sights as inspiring as a dark sky full of stars. Throughout history, our nightly view of the universe has fueled our collective imagination. It has helped give birth to great art and deep insights. But when it comes to the birth of the universe, not even the most creative work of imagination can rival the story that science has now revealed. It's a story that starts with a bang. Welcome to the Big Bang, the energetic outburst at the start of cosmic history that triggered the expansion of space and the creation of all matter. This is our ultimate beginning. The discovery that there was such a beginning is one of the signature triumphs of 20th century science. Now, the challenge to understand it is underway.
Every great civilization in history has its creation story, the explanation that answers the question, how did all of this get here? In some ways, the Big Bang Theory has a lot in common with those stories, because like them, it conjures up a vision of supreme forces and astonishing events beyond human experience. The difference is that the Big Bang story is backed up by evidence, evidence that we can find all around us if we know how to look.
This is Europe's Planck satellite. Launched in 2009, it's an orbiting time traveler that has reached back across more than 13.5 billion years to bring us to the threshold of the Big Bang. Planck has given us the most comprehensive view to date of a crucial turning point when light was first able to move freely through space and carry with it information about how the universe began. To achieve this view, Planck has probed deep into space in every direction, creating a map of the entire sky. But what that map shows is not a familiar scene of stars and galaxies. Rather, it's the faint signal that emanates from the darkness beyond, the cosmic background that lies behind everything else. This is a direct view of the universe when it was only 380,000 years old, just a tiny fraction of its current age. On the face of it, such a view might well seem impossible because it suggests that we can witness something that took place before Earth even existed. But in fact, we can, thanks to the finite speed of light. Light is the fastest thing we know in nature. It travels through space at nearly 300,000 kilometers per second. At that speed, the light we see from the moon takes just 1.3 seconds to reach Earth. That's incredibly fast, but it still means that when we look up at the moon, we are looking into the past, a past that took place on the lunar surface 1.3 seconds ago. The planet Saturn is much farther than the moon, so its light takes longer to reach us. When we gaze at Saturn's rings through a telescope, we are also gazing more than 1 hour back in time. Looking beyond our solar system, the difference between past and present becomes truly dramatic. Here are the Pleiades, a brilliant cluster of stars located some 400 light-years away. That means when we see the Pleiades, we see them not as they are now, but as they once were, 400 years ago, around the time Galileo was recording his first view of the Pleiades through a telescope. But our ability to time travel becomes truly impressive once we peer beyond the boundaries of our own Milky Way galaxy. Here is the Andromeda Galaxy, the most distant object visible to the naked eye. It lies more than 2.5 million light-years away, so our view of Andromeda actually shows what this galaxy looked like 2.5 million years ago. That's long before the first Homo sapiens walked on Earth. Such a span of time is incomprehensible on a human scale. On a cosmic scale, it's a short step. Probing deeper into space with powerful telescopes, we see countless galaxies that are tens or hundreds of millions of light-years away. Today, as we push to the farthest extremes of visibility, we can just make out the light from galaxies that are 12 billion light-years away. Seeing them means we can see more than 90% of the way back to the Big Bang. Beyond this point, there are no more galaxies to observe, because at such a remote and early time, galaxies hadn't formed yet. But we can still look farther, to a time when light came not from stars or galaxies, but from the glowing fog of hot gas that filled the universe in the aftermath of the Big Bang. This is where the Planck satellite has taken us. And it's here that we can find the clues that will lead us to a deeper understanding of the Big Bang. $13.5 billion years ago, our universe looked very different than it does today. This is a time just a few 100,000 years after the Big Bang, when space was filled with particles still too energetic to form atoms. Today, that early stage in cosmic history is imprinted in the heavens, revealed in this detailed map from the Planck satellite. To the eye, the map seems to lack an apparent pattern. But when analyzed mathematically, these colored speckles provide a detailed measurement of the basic properties of the universe and a window onto the Big Bang itself. The key to understanding the map is to realize that it's a record of temperature. It's showing us a universe in the process of cooling down from its white-hot infancy. Red represents distant regions of space that were slightly warmer than average in the remote past, while blue is for those regions that were slightly colder. These differences are like cosmic seeds that allowed matter to accumulate in some pockets of space while leaving others mostly empty. Today, the vast clusters of galaxies we see all around us are the byproducts of this primordial clumping of matter. But if Planck can look back to a time when all of space was filled with a white-hot gas, then why doesn't the sky look white now? The answer to that question challenges one of our deepest intuitions about the universe. The idea that it's always been here. In ancient times, looking into the heavens was like coming face to face with eternity. Perhaps that's because here on Earth, time brings growth and decay. While up above, the stars appear timeless. Aristotle, the most influential of the ancient thinkers, thought he had proved the universe was eternal. For him, the notion that there could be nothing before there was something offended reason itself. But when Isaac Newton discovered his law of gravity, a problem with eternity soon emerged. Because of gravity, the stars must all be attracted to one another. Yet if the universe is eternal, why haven't the stars already converged in one place? That question lingered uncomfortably for more than 2 centuries, right up to the 1920s. By then, there was a new theory of gravity, thanks to Albert Einstein. And astronomers had realized that stars are grouped into galaxies, and that galaxies are scattered through space. But the problem of eternity remained. Over an endless span of time, gravity should have drawn all the galaxies together. To avoid this contradiction, Einstein changed his equations in a way that would exactly counterbalance the influence of gravity across space. But Einstein soon found out that he needn't have bothered. In 1929, following up on earlier work by other astronomers, Edwin Hubble announced that most of the galaxies are moving away from our own. He discovered this by spreading out the light of each galaxy into a spectrum, like a rainbow. Anything that is moving away will appear to emit light that is shifted toward the red end of the spectrum. That's exactly what Hubble saw, and the farther away a galaxy was located, the faster it seemed to be retreating. For Hubble, and for scientists since then, the most logical explanation is that space itself is expanding and pulling the galaxies along with it.
On a human scale, the expansion of the universe is happening too slowly for us to notice. It amounts to every meter of space growing by just the diameter of a single atom every 10 years. That's not enough to overcome the gravity that holds stars together. So the Milky Way isn't getting any bigger, and neither are we.
But in the great void between the galaxies, the expansion of space is adding up. and it means that overall, the galaxies are quickly flying apart. It also means that if we journey back in time, then the galaxies we observe today were once much closer together than they are now. And at some point in the past, there would have been no distinct stars or galaxies at all, just a continuous blaze of hot matter. This is the universe as seen by the Planck satellite. But today, space has expanded so much that the light from this early period has been redshifted beyond the range of the human eye, past the infrared, to ultimately become a signal in the microwave part of the spectrum. That signal was discovered by accident in 1964 when Robert Wilson and Arno Penzias, two radio astronomers from Bell Labs, turned an antenna toward the heavens and couldn't understand why the entire sky was giving off microwaves. Without realizing it, they had discovered the cosmic background, proof that the universe as we know it is not eternal, but had a definite beginning in time. A Big Bang. But there was more to come. As the space age blossomed, so too did the realization that this message from the distant past held the key to our cosmic origins. The Big Bang Theory tells us the universe that we see today was born out of a white-hot mixture of particles that would eventually cool down to make atoms, stars, and galaxies. But because the universe is expanding, that brilliant beginning has faded from view. Luckily, it can still be found in the form of a cosmic background of microwave energy coming from every direction in space. And space is the best place to see it. In 1989, NASA launched COBE, the Cosmic Background Explorer. Its mission was not just to detect the cosmic background, but to see whether it might reveal important details about how the universe evolved. The task was not an easy one. Previous studies with high-altitude aircraft had already shown that the cosmic background is remarkably uniform across the sky. Yet somehow, that uniform glow from the distant past had given way to the very diverse universe we live in now. A universe containing great congregations of galaxies, surrounded by enormous voids of empty space. So, as COBE began to map the entire cosmic background, scientists searched for subtle differences hidden in the smoothness of the ancient universe. What they discovered was a remarkable confirmation of the Big Bang. In this COBE image, the cosmic background appears blotchy, showing very slight differences in temperature on the order of 100,000th of a degree. Scientists were ecstatic. Although these variations were minuscule, they meant that COBE was seeing the earliest hints of large-scale structure in the universe. It also meant that the cosmic background could serve as a link to an even more distant past. Scientists realized the blotches were the traces of momentary fluctuations in energy that occurred when the universe was just a fraction of a second old. But as space rapidly expanded, those tiny fluctuations were stretched to giant size, eventually leaving their mark on the cosmic microwave background. Kobe had revealed the power of the cosmic background as a window into the Big Bang. Now scientists were eager to learn more. Following the success of Kobe, NASA began work on the Wilkinson Microwave Anisotropy Probe, WMAP for short, which was launched in June of 2001. Like Kobe, WMAP was designed to image the entire cosmic background, but it would do so in much greater detail. The stunning result would put to the test theories about how the Big Bang unfolded. For one thing, WMAP confirmed that much of the mass of the universe is in the form of invisible dark matter, consisting of undiscovered particles that are heavier than those that make up stars and galaxies. WMAP brought us a huge step closer toward understanding the Big Bang, but the Planck mission would go even further. Planck was built to survey the cosmic background at more wavelengths and at even higher precision than WMAP. After more than 15 months of scanning, scientists began carefully peeling back the layers in Planck's ultra-sensitive view. First, sources of microwaves that are close by in space had to be subtracted from the image. Next, scientists stripped away all the energy coming from distant sources within the plane of the Milky Way, and from the wispy dust clouds that are pervasive throughout our galaxy. Finally, what remained was the cosmic background itself, seen as never before. The result was a triumph. When it was released in March of 2013, it was clear the new map offered a remarkable portrait of the universe in hard numbers. Among those numbers is the precise age of the universe, which Planck measures at 13.819 billion years old. Planck also provided a detailed breakdown of how the contents of the universe are divided between ordinary matter, including stars and galaxies, dark matter, which gives off no light but accounts for most of the mass in the universe, and a third ingredient called dark energy, which is causing the expansion of space to speed up over time. Such numbers are crucial because they can help cosmologists distinguish between different variants of the Big Bang theory. Today, the dominant idea about how the universe came to be is called inflation. It proposes that in the first trillionth of a second after the Big Bang, the universe expanded exponentially, driven by a release of energy from the vacuum of space. Among other things, inflation explains why the universe looks so similar across great distances in every direction. Scientists working with Planck say that it rules out some versions of inflation, but is consistent with others. However, there are also alternative ideas, including some that say the universe we know today is part of a repeating cosmic cycle. If so, there may have been other universes before this one. To help distinguish between these possibilities, scientists are now searching for signs that gravitational waves produced by the Big Bang left their mark on the cosmic background. Meanwhile, perhaps the most important result from the Planck mission is that across many scales, the cosmic background looks mathematically simple. This in itself may be telling us something deeply profound about the cosmos, a universe that began with a bang, but that has evolved into a symphony of forms and phenomena. A universe that may have started simple, but that has become a truly inspiring place. At a distance of 150 million kilometers from Earth, the Sun is all the star we need. Its energy churns our atmosphere, keeps our oceans liquid, and makes life possible. But imagine if the Sun were more than 3 times larger in our sky and blasting every exposed surface with up to 10 times as much energy. Then Earth would be a very different world, a world ruled by heat and light. A world like Mercury. With its baked and battered surface, Mercury seems like a no man's land among the planets. But it's a no man's land that scientists need to explore.
As the nearest planet to the Sun, Mercury lives in a cosmic hot zone that holds important clues to the origins of our solar system. And it may be our key to understanding conditions on countless alien worlds scattered throughout the galaxy.
For centuries, Mercury eluded astronomers' best efforts to learn its secrets. The reason comes down to geometry. As seen from Earth, the angle between Mercury and the Sun is never more than about 30 degrees. The only way to separate the planet from the Sun's overpowering glare is to look very low toward the horizon immediately after sunset or just before sunrise. Under such conditions, even the largest optical telescopes in the world were not able to show any detail on Mercury's surface, right up until the dawn of the space age. All of that changed with Mariner 10. Launched in 1973, this intrepid spacecraft was designed to fly by Venus. But scientists realized they could get 2 planets for the price of 1 by including Mercury as a second target. During 1974 and 1975, Mariner 10 made 3 separate passes of Mercury, coming to within 327 kilometers of the planet's surface during its 3rd and final approach. During those historic encounters, centuries of speculation were replaced with a stark new picture of the solar system's innermost world. Mariner 10 revealed a heavily cratered planet that looked a lot like Earth's moon. Most of the craters date back billions of years. Because Mercury is too small and too hot to hold on to a thick atmosphere, its surface does not experience erosion from water or wind. Yet hidden in this ancient surface are tantalizing signs that Mercury has changed over the eons. and that despite its outward appearance, Mercury is very different from our moon on the inside. One clue is the planet's surprisingly large mass. Mariner 10 found that Mercury is nearly 5 times more massive than the Moon, even though its diameter is only 40% greater. To be so heavy, Mercury must conceal a huge metallic core, covered by a relatively thin skin of lighter rock. This idea was further reinforced by Mariner 10's discovery that Mercury has a magnetic field. Although it is much weaker than Earth's, the presence of the field suggests that at least part of Mercury's core is still in a molten state. Mariner 10 tried to glean further clues from its reconnaissance of Mercury, but during its 3 brief passes, the spacecraft imaged less than half of the planet's surface, and what it found left many unanswered questions. Clearly, another mission to Mercury was needed, one designed for a much longer stay. But even though Mercury beckoned, the dream of returning would remain unfulfilled for nearly 30 years. At last, on August 3, 2004, NASA's Messenger spacecraft set out to become the first planetary probe to orbit Mercury and reveal its features and characteristics in detail. But just getting there would be half the challenge. Mercury is much closer to Earth than most of the other planets in our solar system, but it also sits deep within the Sun's gravitational field, which causes it to travel through space at a drastically different speed, roughly 65,000 kilometers per hour faster than Earth. In order to put itself in orbit around Mercury, rather than just sail by, Messenger would first have to match its speed to the planet's. Paradoxically, that meant the spacecraft would have to lose energy to allow it to gradually spiral in closer to the Sun. The journey would take over 6.5 years. Along the way, Messenger passed near to Mercury on 3 separate occasions, giving scientists a chance to test the probe's cameras and sensors. The results were spectacular, but the fleeting glimpses only whet scientists' appetite for more data. Finally, in March 2011, Messenger approached Mercury for a 4th and final time, this time moving at just the right speed to be captured by the planet's gravitational pull. The long-awaited exploration of the solar system's innermost planet was set to begin. Thanks to Messenger, Mercury was finally getting its moment in the Sun. Elusive and fast-moving in the twilight sky, the planet Mercury was named by ancient astronomers after the messenger of the gods. But not until 2011 would NASA's own Messenger mission be in a position to reveal one of the least explored worlds in the solar system. Messenger came well equipped for the job. The sunlight at Mercury is so intense it would easily fry an unprotected spacecraft. So Messenger is covered in thermal insulation, and it carries a built-in system of radiators that are designed to draw heat away from its sensitive electronics. 2/3 of the surface area of its solar panels are mirrored to deflect rather than absorb solar energy and help control temperature. Finally, the main body of the spacecraft remains hidden from direct sunlight by a large sunshade made of ceramic cloth on a lightweight titanium frame. While the outer surface of the sunshade can reach 370 degrees Celsius, hot enough to melt lead, behind this essential barrier, the spacecraft operates at room temperature. Scientists expected the measures would be enough for Messenger to survive at least a year in the hostile environment around Mercury. But as Messenger began revealing the planet's complex geology, they were soon hoping for more. With both a wide and a narrow-angle camera, Messenger would be able to map the entire surface of Mercury down to features 1 kilometer across and zoom in on areas of special interest to see details as small as 20 meters across. The camera system could also be used to reveal slight color differences in Mercury's rocky terrain that would otherwise be too subtle for human eyes to discern. This would prove useful for reconstructing the multi-layered history exposed by Mercury's craters, and there were many craters to look at.
On the Moon, there's a long-standing tradition that craters are named after scientists and philosophers. On Mercury, it was decided instead that craters should be named after famous artists, composers, and authors. But while Mercury's craters may all have the arts in common, Messenger soon discovered some striking differences among them.
Here, Messenger zooms in on 2 craters, Degas and Bronte, located side by side. To the human eye, they seem identical in color, but Messenger reveals that Degas looks bluish relative to the brownish color of Bronte. This difference suggests that Mercury's surface includes layers of rock with different compositions. In this case, the impact has punched through a bluer colored rock underlying the brown. Elsewhere, the color differences are more complex, pointing to a rich and diverse geologic history that was not apparent to scientists before Messenger arrived. Sometimes, the effect of an asteroid or comet strike is obvious because it scatters material in bright rays across an older set of features. But not every part of Mercury's surface is shaped by an impact from above. In this intriguing image, a smudge of orange stands out against a darker colored landscape. Seen up close in black and white, the object at the center of the smudge looks like a tall peak inside a crater. But this is no ordinary crater. It's the likely scene of a volcanic eruption that sprayed out orange-colored material from deep within the planet's interior. Messenger has confirmed that Mercury is covered with features like this one that could only have resulted from volcanic activity. Here, a crater named Faulkner looks half-sunken into the landscape. The crater was probably flooded by lava, which topped its ancient rim and half-filled it with molten rock. Elsewhere, the large crater Rachmaninoff features a double rim, with the outer ring measuring more than 30 kilometers across. Color differences show that lava flooded the center of the crater long after it formed, and then spilled over into the region between the inner and outer ring. In other cases, the colors on Mercury's surface are harder to interpret. For example, some crater floors have bright hollows, which stand out against the darker rock and are completely unlike anything seen on the Moon. The exact nature of these bright patches remains a mystery, but scientists suspect they may be the result of some minerals becoming gaseous under the sun's intense glare. One area where Mercury's color is especially revealing is the Caloris Basin. At 1,500 kilometers across, it is by far the largest impact feature on the planet. Caloris formed in the first billion years of the solar system's history, when a very large asteroid struck Mercury. Over time, other smaller craters scarred the basin. Then, lava covered the basin's vast central plain, leaving the raised rims of the smaller craters to stand out like blue islands. In contrast, the edge of the giant basin is marked with orange spots, where hot lava found a path to the surface through the shattered bedrock. Meanwhile, at the center of the Caloris Basin, Messenger has discovered a strange network of troughs that spread spider-like across the basin floor. These are indications that the surface of the basin may have been pulled or stretched in the past. With its oversized metallic core, there seems little doubt now that Mercury was once a geologically active planet, and that it remained so long after its formation. Now, aided by Messenger's trove of images and data, scientists are gaining a deeper understanding of the hidden forces that lie below Mercury's pockmarked surface. Hundreds of light years from Earth, a newly discovered world basks in the fierce light of an alien sun. This is one of scores of planets uncovered by NASA's Kepler mission, which was designed to hunt for worlds like Earth. Small, rocky, and at just the right distance from their stars to allow for the presence of liquid water. But in the course of its search, Kepler has also found many planets that are more like Mercury, orbiting much closer to their stars. Long neglected by planetary explorers, Mercury has now become our best reference point for understanding countless other hot worlds that populate our galaxy in the billions. And of special interest to scientists are those features on Mercury that are found nowhere else in the solar system. Features like towering cliffs that snake across Mercury's battered terrain for hundreds of kilometers. Here, one such cliff slices the ancient crater Rameau in half, leaving one side of the crater 2 full kilometers higher than the other. Having imaged the entire surface of Mercury, NASA's Messenger spacecraft has confirmed that cliffs like these are widespread around the planet. It's now believed that they formed when Mercury's giant metallic core cooled and gradually shrank. This left the planet with an outer skin that was too large. As the interior grew smaller, the surface buckled, forming cliffs like giant wrinkles in a planet-wide shrink wrap. The cliffs are an example of how Mercury's outer appearance has been shaped by internal forces. And as scientists combine Messenger data with ground-based radar measurements, the true nature of Mercury's dynamic interior is now coming into focus. A key discovery is that Mercury's metallic core is even larger than expected, accounting for 85% of the planet's total diameter. But while the inner portion of the core is likely made of solid iron, like Earth's, at least some portion of the outer core must be liquid. It is the motions within this electrically charged liquid that are responsible for generating Mercury's magnetic field. However, this picture presents scientists with a dilemma. If Mercury's core is made only of iron, it should have completely solidified by now. Since the smaller the planet, the more quickly internal heat escapes, even for a planet as hot as Mercury. This has led researchers to speculate that lighter elements, like silicon and sulfur, are present in Mercury's core in significant amounts. That would lower the core's melting point and leave the outer portion liquid. Mercury's liquid core may even be surrounded by a shell of solid iron sulfide, something not seen on any other planet. But while this explanation satisfies all the data, it leads to a larger mystery. In order to explain why Mercury's core is so large, scientists have speculated that Mercury was once more like Earth or Venus, a larger planet with a thick rocky mantle surrounding its core. Then, an enormous collision with another object blasted off much of that mantle, leaving the core intact. Another theory suggests that in the very early days of the solar system, the sun went through a much hotter phase and boiled off some of Mercury's mantle with its intense heat. But the latest findings challenge both of these theories. Instead, it may be that Mercury formed as it is now, small but rich in lighter elements that were once thought not to have been abundant so close to the sun. Whatever the explanation, it's clear there's something about Mercury's history and about the formation of the solar system as a whole that we don't yet understand. And that's not the only way that Mercury is defying expectations, because here, on a world so thoroughly baked by the sun, Messenger has also discovered ice. As hard as this is to imagine, scientists already had hints that there was ice on Mercury, because radar observations indicated there is a highly reflective material somewhere near the planet's north and south poles. Mercury's poles are where we find deep craters whose bottoms remain in perpetual darkness as Mercury rotates on its axis. Shielded from direct sunlight, these craters are like cold traps for water vapor brought to Mercury by incoming comets that collide with the planet's surface. Although Messenger's cameras cannot see into these dark-bottomed craters, Messenger detected the presence of ice with a device called a neutron spectrometer, which measures how much the ice absorbs the energy of incoming cosmic rays. The data suggest there could be up to 1 trillion tons of ice on Mercury, to a depth of several meters. If so, the ice makes a tantalizing target for future explorations of the planet's surface. Again and again, Mercury has proved to be an astonishing place. Not just a hotter version of our moon, but a fascinating world in its own right, with a history that is crucial to our understanding of rocky planets everywhere. That is why the European and Japanese space agencies have now joined forces to send another mission to Mercury, which is scheduled to arrive early in the next decade. Once, Mercury was the least understood of planets. Today, it has become one of the most interesting, and the ambassador of a vast and emerging population of newfound worlds that together make up the cosmic hot zone. Far out in the Milky Way, a tiny particle of matter flies like a bullet through the vacuum of space. Propelled by colossal forces, the particle moves at nearly the speed of light, zipping by stars and the glowing clouds of gas where stars are born. Suddenly, a planet looms directly in front. Unstoppable, the high-energy particle rips into the planet's atmosphere. It collides with a nitrogen atom, destroying both the particle and the atom in a flash of pure energy. Now that energy creates new particles, which cascade downward, causing more collisions as they go. Soon, thousands, then millions of more particles spread out in a widening cone and then slam into the planet's surface. Earth has just been hit by a cosmic ray. During the past century, astronomers have come up with a multitude of ways to get information from the universe. Stars give off visible light, but they also give off infrared, ultraviolet, X-rays, and other forms of light our eyes can't see. What makes cosmic rays so interesting is that they're not another form of light.
They're bits of matter that are coming directly to us from deep space. Cosmic rays carry information about powerful forces and events taking place thousands or even millions of light years away. But to understand what cosmic rays can tell us about the universe, we need to know how they are produced. In fact, it took a while for scientists to understand that cosmic rays even exist. The idea has its roots in the discovery of radioactivity by the French physicist Henri Becquerel in 1896. Radioactivity is the particle radiation that comes from atoms breaking apart spontaneously in the environment. When it was discovered, scientists realized that radioactivity might explain why they could never get an object to hold on to its static electric charge indefinitely. Because of radioactivity, in rocks and soil, there are always particles present near Earth's surface. Those particles can interact with anything that has an electric charge, causing that charge to gradually leak away. Over a century ago, scientists predicted this effect would disappear if they could take an electrically charged object away from Earth's natural radioactivity at the surface. The only question was how. The answer would come in 1911, when Victor Hess, a physicist from Austria, began a series of daring balloon flights that would eventually carry him and his instruments to a height of over 5 kilometers, roughly half the cruising altitude of a commercial jet airliner. As he ascended, Hess measured the presence of charged particle radiation like the kind produced by radioactive materials. At first, the radiation diminished with height, exactly as expected. But then there was a surprise. Starting around 1,500 meters, the situation reversed. Hess found there was more radiation than at sea level, and it was growing with altitude. By the time Hess landed, there was no longer any doubt. Earth was bathed in radiation coming from above, and a new field of science was born. Scientists eventually started calling the mysterious space radiation cosmic rays. By the 1930s, the invention of the Geiger counter had made it clear that cosmic rays were pummeling Earth at an astonishing rate, amounting to tens of thousands of incoming particles per square meter every second. Most of the particles were relatively low in energy, but some had enough energy to pass through rock, or even up to a meter of lead. Then, in 1938, the French physicist Pierre Auger took some Geiger counters high up into the Alps to measure cosmic rays there. He found that when two Geiger counters were set far apart, they sometimes recorded cosmic rays arriving at exactly the same time. Auger had discovered cosmic ray showers, bursts of particles that rained down in a widening spray, following the destruction of a single, much more energetic particle higher up in the atmosphere. Based on the size of those showers, some of the cosmic rays coming in from deep space were clearly more energetic than any particle produced on Earth. Now, scientists found themselves embarking on a new quest to understand where in the universe those energetic particles were coming from. Thousands of light years from Earth, a massive star ends its life in a brilliant explosion.
This is a supernova, a stellar cataclysm that is one of the most energetic phenomena in nature. As the powerful shockwave expands, it creates a wreath of glowing gas, like this one, called Cassiopeia A, here revealed in striking detail by the Hubble Space Telescope. But could such an event also give rise to cosmic rays?
The riddle of cosmic rays is one that's being solved in stages. The ultimate goal remains understanding how these high-energy particles from beyond our solar system are created. But to get there, scientists first had to figure out what kind of particles they were.
For the most part, those particles never reach us here on the ground. Instead, they strike the atmosphere and unleash a torrent of secondary particles that shower down like so much subatomic shrapnel. By studying these secondary particles in the 1930s and 40s, scientists gradually narrowed in on the true nature of cosmic rays. What they found is that most cosmic rays, about 90% of them, must be single protons. Protons are positively charged particles that are part of every atom in the universe, but most of them occur in the form of hydrogen atoms. Atoms that are made of a single proton orbited by a single electron. Hydrogen is the most abundant element in nature. Stars are mostly composed of hydrogen, and so are the vast clouds of gas out of which new stars form. So whatever is making cosmic rays and sending them our way, it has plenty of raw material to work with. In 1947, a high-altitude balloon experiment revealed that most of the remaining 10% of cosmic rays are made of the nuclei of heavy atoms, like iron. Like protons, these atomic nuclei are stripped of their electrons, and they've been sent rocketing through space by a powerful force. But what? Even solar flares, the giant explosions that erupt from the surface of the sun, cannot account for the energies behind these heavier cosmic rays. But solar flares do offer us a hint about how cosmic rays are created. Because solar flares are caused by the release of magnetic energy. Under the right circumstances, a magnetic field can be used to accelerate an electrically charged particle, like a proton, to enormous speeds. Today, this principle is at work in the Large Hadron Collider, the world's largest particle accelerator, where huge superconducting magnets are used to send protons careening around a giant ring 27 kilometers in circumference. When the protons collide, the energy release is enormous, generating new particles that allow scientists to explore the fundamental properties of matter. Amazingly, some of the highest energy cosmic rays are millions of times more energetic than the protons in the Large Hadron Collider. It means that somewhere out there in space, nature has created its own particle accelerators that would dwarf anything humans have built on Earth. But identifying them has proved a major challenge. Starting in the 1980s, an experiment called Fly's Eye in the remote Utah desert used sensitive detectors to spot the faint ultraviolet glow of cosmic ray air showers high up in the atmosphere. This allowed researchers to see what direction any particular cosmic ray was coming from in the sky. Yet, this did not help scientists figure out where cosmic rays ultimately come from. The reason is that the space between the stars is a complex network of magnetic fields that thread their way around our galaxy. And these fields have been bent and twisted by the turbulent motions of ionized interstellar gas. The magnetic fields completely scramble the directions of cosmic rays moving through the galaxy, so that from Earth's point of view, they appear to be coming from all over the sky, leaving no hint about where they originally came from. In their efforts to explain cosmic rays, scientists had run into a significant roadblock, one that would require them to search the heavens in a new and different way. This is our Milky Way galaxy, home to hundreds of billions of stars and vast clouds of dust and gas that stretch on for thousands of light years. It is a huge and complex system. And hidden somewhere within its depths are the sources of high-energy particles we call cosmic rays. As early as 1949, the nuclear physicist Enrico Fermi proposed the idea that cosmic rays are produced when protons and other charged particles are accelerated to high speeds by bouncing around within a changing magnetic field. But where in the galaxy might conditions make such bouncing around possible? Because cosmic ray particles are intensely energetic, the sources that create them must be able to somehow provide that energy. And those sources may also give themselves away by throwing off a high-energy form of light called X-rays. Here on Earth, X-rays from space are absorbed by our atmosphere, so X-ray telescopes must do their work orbiting high above Earth's surface. Today, the Chandra X-ray Observatory is our most discerning X-ray eye on the sky. Chandra has been used to peer into some of the hottest and most energetic regions of the galaxy, revealing views like this of the Carina Nebula, where interstellar gas is cooked to millions of degrees by newborn giant stars. This is a high-energy environment, but not one that has the kind of magnetic fields needed to accelerate cosmic ray particles. So instead of looking at places where stars are born, cosmic ray hunters have zeroed in on those places where giant stars have died violently. This spectacular ring is the remnant of a supernova, a vast stellar explosion that sprays matter outward in all directions, creating a rapidly expanding shockwave. The leading edge of this bubble can move at tens of thousands of kilometers per second, but that's still nowhere near the speed of a cosmic ray particle. However, scientists after Fermi realized that supernova shockwaves can compress and strengthen magnetic fields in the surrounding gas. Then, charged particles moving back and forth across the shockwave can pick up more and more energy through a process called Fermi acceleration. Eventually, the particles would be moving fast enough to break away from the shockwave and fly off into the galaxy. Here at last was a theory that could explain cosmic rays, but proving it would require another kind of space observatory. Fittingly, that observatory is NASA's Fermi Space Telescope. Named after Enrico Fermi, it has special detectors that can pick up gamma rays, a form of light even more energetic than X-rays.
5, 4, 3. Engine
Launched
start.
in 2008, the Fermi telescope had been used to study the most extreme phenomena in the universe,
A gamma-ray telescope searching for unseen physics in the stars.
like the supermassive black holes that lie at the centers of distant galaxies, or mysterious explosions known as gamma-ray bursts. And Fermi has also turned its attention to two of the most interesting supernova remnants in the Milky Way. One is W44, a dramatic shell of expanding gas located 10,000 light-years away in the constellation Aquila the Eagle. The other is IC443, nicknamed the Jellyfish Nebula. It lies roughly 5,000 light-years away in the constellation Gemini. What these two colorful bubbles have in common is that they are both the result of supernova explosions expanding into dense clouds of interstellar gas. In theory, this should be the perfect situation for generating cosmic rays by Fermi acceleration. The Fermi spacecraft is the perfect tool for testing this idea. Its sensitive detectors can distinguish between gamma rays that are produced by different kinds of physical processes. But it would take more than 4 years of gathering data with Fermi for scientists to be sure. Finally, in February 2013, they were ready to reveal their results. What they had found was a clear signal, the first ever seen, of protons at high energies occasionally colliding to produce gamma rays. The type of signal exactly matched what was expected if the protons were being accelerated on their way to becoming cosmic rays. 100 years after cosmic rays were first discovered, the Fermi telescope had finally captured a glimpse of cosmic ray creation. Scientists now know more about cosmic rays than ever before, but the search doesn't end here. Although they are rare, the highest energy cosmic rays are so powerful, even a supernova shockwave isn't enough to drive them. So now the search for new sources of cosmic rays is reaching beyond the boundaries of the Milky Way. This is M87, a giant galaxy about 60 million light-years from our own. Deep in its core lies a black hole so huge its mass is equivalent to more than 6 billion suns. As it devours gas from the surrounding environment, the rapid spin of the black hole causes some of the gas to escape, forming a jet that extends hundreds of thousands of light-years into intergalactic space. The jet is wrapped in magnetic fields that may just be strong enough to create what are known as ultra-high energy cosmic rays. Because they are so rare, the experiments that hunt for these particles are huge, covering thousands of square kilometers in an effort to capture just a handful of the most energetic particles in nature. But if the theory proves correct, for the first time, these experiments may be able to prove that we are being hit by matter from another galaxy. Thanks to the discovery of cosmic rays, we know we have a direct connection to some of the most powerful phenomena in the universe. Now, as a new chapter of exploration opens before us, we are learning just how astonishing that link to the cosmos may prove to be. It's the summer of 1950, and at the U.S. government laboratory in Los Alamos, New Mexico, scientists are breaking for lunch. 5 years earlier, this was the home of the Manhattan Project, the top-secret effort to build the first atomic bomb. But now, in a lighter moment, the discussion at one table has turned to flying saucers. It begins with a humorous story involving aliens. But soon the scientists are debating when it might be possible to travel to the stars. Among those present is Enrico Fermi, a Nobel Prize-winning physicist whose many contributions included developing the world's first working nuclear reactor. After a while, the conversation turns to more earthly topics. Then, out of the blue, Fermi suddenly blurts out a question. Where is everybody? Fermi was still thinking about extraterrestrials, and he had just realized that something wasn't right. Fermi then did some quick calculations on the spot that confirmed his suspicions. If there were advanced extraterrestrial civilizations elsewhere in the galaxy, it's likely we would have picked up some sign of them by now. Maybe signs of several civilizations. The fact that it hasn't happened is now called the Fermi paradox, after the man who posed the question.
Fermi wasn't the first person to wonder why we haven't yet seen any signs of alien life in the universe. But as a gifted scientist, he framed the problem in a way that would resonate far beyond that lunchtime conversation.
Over 6 decades later, the Fermi paradox remains unsolved, even as the evidence has mounted that the basic ingredients for life, including carbon, oxygen, and nitrogen, are among the most common elements in the galaxy. Astronomers have also discovered hundreds of planets beyond our solar system and directly observed the swirling disks around young stars where new planets are forming right now. All of these new data continue to suggest that if life happened once, right here, it must have happened many times, increasing our chances of contacting an advanced civilization. This optimistic reasoning is further bolstered by the fact that life on Earth has a long history. We know from fossils that over the eons, many different kinds of creatures have called this world home, and that evolution has been very effective at ensuring that life continues to adapt and flourish with changing conditions. The earliest traces of life come not from fossils, but from microscopic patterns and chemical traces in ancient rocks. These show that bacteria were already living on our planet at least as early as 3.5 billion years ago. And that means the first cells and the first DNA must date back even earlier. Earth itself is no more than 4.6 billion years old. That's how long ago it formed, along with the other planets, out of the leftover debris that surrounded an infant sun. After allowing a few 100 million years for Earth's surface to cool and its atmosphere to stabilize, it seems that life must have appeared here almost as soon as it was possible to do so. The key ingredient was water. In liquid form, water is an ideal solvent, where molecules that are important to biology can interact and react. Because of the early and sustained presence of liquid water, life was able to gain a foothold on Earth. And it may be that Earth was not alone. 2012, NASA's Curiosity rover landed at Gale Crater on Mars. Over the next several months, as it meandered along the crater's dusty floor, Curiosity found convincing evidence that the rock beneath its wheels had formed in standing water. The presence of clay minerals in the rock suggests that the water was similar to fresh water on Earth and hospitable for life. That's a long way from showing that there once was life on Mars, but it does mean that for some period of time in the remote past, Mars was a livable planet, at least livable for microorganisms. Some suspect there could still be Martian life today, eking out an existence deep underground. So in our own solar system, it appears life arose in one or possibly both of the places where there was an environment that could sustain it. Even if Mars is a dead world, that's a 50% score. And in a galaxy filled with billions of planets, it's hard to imagine that life hasn't been equally successful out there among the stars. But as Fermi realized, there must be a hitch. Perhaps it was only a matter of looking for ET in the right way. By peering deep into the universe, astronomers have come face to face with the immensity of time. Observations of distant galaxies reveal that we live in an expanding universe. By measuring the rate of the expansion, cosmologists now estimate our universe began with an event called the Big Bang, which took place some 13.8 billion years ago. Our deepest views of the cosmos also reveal that by 500 million years after the Big Bang, the formation of stars and galaxies was well underway. If so, our own galaxy probably started forming about that time. In contrast, our solar system is less than 5 billion years old. It has been around for less than half the age of the Milky Way. This would seem to suggest that there has been plenty of time for other civilizations to arise within the Milky Way long before our own. So when it comes to finding someone else out there that we can talk to, time should be on our side. Instead, we have the Fermi paradox, the startling puzzle that asks, if life is so abundant on Earth, and if the galaxy has been around for such a long time, why have we not yet seen any sign of anyone out there? In 1950, Fermi's question was originally triggered by a conversation among physicists about traveling to the stars. But even if interstellar travel is impossible or impractical because of the great distances involved, the Fermi paradox still holds. That's because the technology already exists to probe the galaxy for radio signals from extraterrestrials. Around the time that Fermi asked his famous question, astronomers were already planning the construction of giant radio dishes to probe the heavens. For the first time in history, humanity had an ear on the cosmos. By 1960, American astronomer Frank Drake was using a 26-meter dish in Green Bank, West Virginia, to listen for any radio emissions that might be coming from alien civilizations. It was the beginning of SETI, the search for extraterrestrial intelligence. Drake was not expecting to hear a message specifically meant for us, but he knew Earth was sending out plenty of signals in the form of commercial broadcasts and military radar. A civilization even slightly more advanced than our own might be giving off far more. Right from the start, SETI presented a huge needle in the haystack problem. It was one thing to have the right sort of antenna for listening in on ET, but quite another to know where to point it and which of the billions of possible frequencies to listen to. Drake's approach was to point at a couple of the nearest stars that seemed similar to our Sun and to choose frequencies near 1420 megahertz, the frequency of radio waves emitted by hydrogen, the most common atom in the universe.
When Frank Drake began his search, enthusiasm for SETI was building. Since no one had looked before, it was possible that the skies would turn out to be flooded with signals from well-established civilizations, all talking to each other in a galactic social network. Maybe the answer to the Fermi paradox was simply a matter of switching on a radio receiver.
But that's not what happened. Drake's initial search came up empty. And so has every subsequent effort to pick up alien radio signals, at least so far. Among the most extensive was Project Phoenix, which used radio dishes in Australia and the United States to probe some 800 carefully chosen star systems. After the project wrapped up in 2004, scientists concluded that if an advanced civilization was using radio transmission to announce its presence anywhere within 200 light years of Earth, we would have discovered it by now. In comparison, the Milky Way is more than 100,000 light years across, so there's still plenty of galaxy left to search. But our ability to gather and sift through radio signals from space is rapidly growing more efficient, driven mainly by Moore's law, which projects a doubling in computer processing speed about every 18 months. In California, scientists at the SETI Institute are developing the Allen Telescope Array to vastly improve the speed and volume of radio-based searches. If technology continues to improve at its current rate, then by the middle of this century, humans will have listened in on more than 1 million star systems. If no alien civilization turns up by then, Fermi's paradox will be a more pressing problem than ever. And we'll be left to consider why the chemical and biological processes that led to our emergence has not been repeated elsewhere, or at least not often enough for us to find anyone out there to talk to. Our existence on Earth proves that life is possible in the universe. What it doesn't tell us is how probable life is. For 4 years, starting in 2009, NASA's Kepler spacecraft found evidence for thousands of planets in the small section of the sky where it trained its gaze. Although many of these finds still need to be confirmed with follow-up observations, the numbers suggest that across the Milky Way there are tens of billions of planets similar in size to Earth. But we also know there cannot be billions of civilizations out there trying to make contact with us, or we would have heard from some of them already. Where are they is the way Enrico Fermi once framed the question. Given the potential for so many civilizations in our galaxy, is it really plausible that we could be alone? Over the decades since Fermi posed his famous paradox, there have been many attempts to resolve it. One set of explanations explores the possibility that extraterrestrials exist, but that they either can't or won't communicate with us. For example, there may be intelligent life on other planets without advanced technology, or in an environment, perhaps underwater, where radio communication is not practical. We may also be overestimating the interest that alien civilizations may have in contacting us. As societies become more advanced, perhaps they also become more inward-looking. Some have suggested that aliens are well aware of us, but they're monitoring us quietly, like scientists studying another species in their natural setting. The trouble with all these speculations is that for every society we can imagine that doesn't want to say hello for some reason, we can also imagine others that do. For us, curiosity and communication have come with huge survival benefits. The more information we can gather about our environment, the better we can prepare for unknown threats or take advantage of resources that come our way. It stands to reason that at least some extraterrestrial civilizations must be curious and interested in communicating. We can even imagine that such a civilization would be sending probes out to the stars. In 2013, Voyager 1 became the first human-made probe to reach the edge of the solar system and cross into interstellar space. With a few centuries of improvements to our technology, we could be sending much faster and more sophisticated probes to the stars. These probes could be equipped with instructions for how to find a moon or asteroid with suitable resources for the probes to make copies of themselves that would be sent to explore further. The idea of a self-replicating machine was first suggested by the mathematician and computer science pioneer John von Neumann. If such machines could be built to travel through space at 1/40th the speed of light, about 400 times faster than Voyager 1, after a few million years, they would have visited every star system in the Milky Way. But that's just the blink of an eye in the lifetime of our planet. The fact that we have found no evidence for von Neumann machines in our solar system suggests that no one has ever built them, which in turn means that there can't be many advanced civilizations out there, or someone would have done it by now. This kind of reasoning has focused attention on the history of life on our world, and the remarkable chain of coincidences that has given our species virtual mastery over our entire planet. Perhaps we are more special than we think. Some have noted that even though life emerged quickly on Earth, complex multicellular life took billions of years to show up. If a planet can't maintain a stable environment for that long, then maybe the best it can manage is to be home to a world of bacteria. In 2000, astronomer Don Brownlee and paleontologist Peter Ward looked at how many things have to go right to have a planet like Earth. They concluded that while simple life may be very common throughout the universe, complex life is an exception. They called their idea the rare Earth hypothesis, and in the next decade or so, we may have a hint about whether they're right. Following on from the Kepler mission, scientists at the Massachusetts Institute of Technology are now developing the Transiting Exoplanet Survey Satellite, or TESS for short. Its goal will be to spot Earth-like planets crossing in front of nearby stars. If there is life on those planets, even microbial life, follow-up observations may detect traces of it just by analyzing the starlight passing through the planet's atmosphere. If TESS turns up planets that may be hospitable to bacteria, but nothing more, then we may indeed be living in a rare Earth kind of universe.
Of course, there is one more way of resolving the Fermi paradox, and that is to consider that the technology needed to make contact with another civilization may go hand in hand with the technology that would allow a civilization to self-destruct. So far, we've managed to avoid blowing ourselves up. But given the increasing pressure we're putting on our planet, it's fair to say our survival is far from guaranteed.
One of the great ironies of the Fermi paradox is that it came up in a conversation between brilliant scientists working in a military lab at the height of the Cold War. That should remind us that the paradox is not just a curious quirk of the cosmos, but an important caution for our entire civilization. If nothing else, Fermi's paradox tells us that long-lasting civilizations may be exceptionally rare, and that it will take great perseverance on our part if we are to become one of them. If we succeed, and then we do one day pick up a message from another intelligent species, we will have double reason to celebrate. It will mean that we're not alone, and that thanks to our careful self-preservation, neither are they.